Hey guys. Oh, weird hair. Okay. So this is our lesson 7.3 part 2. We're going to be graphing the logarithmic functions today. So the first thing I want to do is think about a graph that we do know a lot about, which is graphing the exponentials. And we learned in the last lesson that the exponentials and the logarithms are inverses of each other. So we also know a bunch of things about inverses, and we're going to put all these thoughts together to figure out what the heck does a logarithm look like. And I know usually our first idea for graphing is to grab a graphing calculator and go to town. It's not a good idea today because while your graphing calculator is amazing, it does a horrible job of graphing logarithms. So we'll talk about why later on. Okay. Ugh. Well, first of all, let's get my face out of the way. We have an exponential of 10 to the x power. And we learned when we're graphing exponentials, we usually grab the calculator and just plug in whatever x's we want. Well, I'm going to mentally figure out the numbers because right now I'm too lazy to grab my calculator. I can choose any x's I want. I'm going to go with the old sturdy -1, 0, 1, and 2. Let's go get crazy. All right. So if I were to plug in -1, 10 to the negative first power is a 1/10. And again, you could have just typed that into y1 and gone to your table. And maybe I will do that. But for now, I'm going to use my brain. Plugging in a 0, 10 to the 0 is a 1. 10 to the first is obviously a 10. And then 10 squared is a 100. That's why I was kind of cringing. I was like, 100? I'm not going to be able to graph that, y'all. Okay, so if I go to graph each of these ordered pairs as best I can, it's not going to be very good. You've seen my graphs, right? So this guy is -1 and then just above the axes, 0, 1, 1, 10, and then something I cannot graph. But we remember from our work with exponentials that Mrs. Abruzzo cannot graph them, but that's about as good as I can get. All right. So one thing to notice is the y-intercept that we can clearly identify there is at 0, 1. There is most definitely an asymptote here at y = 0. The cool thing about these is the domain always had a -infinity to a +infinity domain. Those are for exponentials. The range was affected by where the asymptote was. So if this guy had an asymptote at y = 0, that was the start of the range. So it went from 0 to infinity. Oh, I don't know what happened here. This isn't supposed to be here. None of that's supposed to be here. I don't know what happened. I must have copied this before I fixed it. My bad. All right, moving on. Logarithm. I have no idea. Okay, I know a few things. First of all, this is a common logarithm, right? So this is a logarithm base 10. Now the other thing I know is that the logarithm base 10 and base 10 exponential, these are inverses of each other, right? These are inverses. Okay, now I got to go back in my brain and remember, what does it mean to be an inverse? It means all of your xy ordered pairs are going to switch. That was like the major thing with inverses. Your x's and y's switch, right? So this guy, instead of being at -1, 0.1, it'll be at 0.1, -1. And then same thing here. Instead of being at 0, 1, it'll be at 1, 0. So I'm just kind of doing this. Instead of at 110, it'll be at 10, 1. And then the one I couldn't graph anyways will now be at 100, 2. I'm still not going to be able to graph that, okay? So let's take a look. If I were to graph 0.1, -1, it's like right there, kind of, not really. And then 1, 0, and then 10, 1. And that doesn't really give me a lot to work with. Now, the other thing I want you to remember about inverses is they reflect across the line y = x. Wow, that is not straight at all. Okay, got a little weird there. So if I think about taking that blue shape and reflecting it down across that green line, wouldn't it create this? Nope, it wouldn't, Abruzzo, because that's the worst graph you've ever done in your whole life. Okay, it kind of creates that shape, all right? My friends, this is what a logarithm looks like. At least a logarithm with a base that's greater than 1. Let's talk about some things here. And remember, I got a weird table here. I don't know what's going on. This is just garbage. Abruzzo, Should have proofread this. Okay, think about everything we know about inverses. The intercept, well, this time we have an x-intercept instead of a y-intercept, because if you look here, I got an intercept at 1, 0. The asymptote, well, it was at y equals 0 on the exponential, so it now makes sense that I have what's called a vertical asymptote at x equals 0. Remember, one of the properties of inverses was that the domain and range will switch. So the domain is now parentheses 0 to infinity, but the range is the one that goes forever. So logarithms and exponentials are closely related in a sense because they are inverses of each other. Wow, that's something to think about. Okay, let me show you what the calculator does. So if I tried to type the common log of x and graph it, let's get rid of that old stuff. All right, so type common log, which is log, and then x. Remember, that's base 10. That's what my calculator thinks it looks like. And this is why we can't really use the technology, because the calculator basically stops being able to graph points. Like, it gets so small that it's like, I can't, I give up. So it doesn't even show you this little, woo, well, okay. You get the idea. It doesn't show you that little tail that swoops down along the asymptote. So that's why we can't rely on our technology to graph really good logarithms, unless we're smarter than the technology and we kind of understand that where that vertical asymptote is, there should be like this tail swooping down. Okay, that's what I need to see from you guys when we're graphing these. So let's take a look at this one. We have a common logarithm of x plus 4. And if you want to get a little bit of tech assistance, we can do that. So x plus 4. Now, if we were in class, I'd be asking you guys to make some predictions. What do you think happened here? And I would hope you'd all shout out, well, Mrs. Abruzzo, it was shifted horizontally to the left 4. Is that what you were going to tell me? Because it was. Now let's think about what that means for our graph. Because it was shifted, and it is to the left 4, because there's that built-in negative in math, that vertical asymptote, which normally was at x equals 0, that has been shifted to the left 4 as well. So now you have a vertical asymptote at x equals negative 4. Now we saw on our calculator not a whole lot of help. Like if I go to my table, that's not what I wanted to do. Hold on, I'm going to get rid of that. If I go to my table, there's a whole lot of errors, and then the only point that occurs after the error is the only good point I can graph. Well, there's probably one later on. So there's negative 3, 0, and 6, 1. All right. So 6, 1, negative 3, 0. But this surely is not a logarithm, this little piece here, because we have to remember our calculator isn't going to show us that tail that swoops down. There we go. Kind of. That's what the graph looks like for that logarithm. The domain actually goes all the way up until negative 4. It bumps along negative 4. It doesn't quite get there. So we're going to say our domain starts at negative 4 with a parenthesis and then goes to the right forever. So remember, domain is left to right. So that one's a little weird, right? The range is the one that's easy today. The range is going to go forever low and forever high. So opposite of what we saw with the exponential graphs, which makes sense because we just said they're inverses. So another thing to think about on your calculator is if your asymptote is at an integer, which for Algebra 2 they will all be integers, the first time you see an error will be the location of the asymptote. So right here, this is the first time I see an error, which means negative 4 is the asymptote. It's the vertical asymptote, but you want to write it as an equation, x equals negative 4. Okay? Food for thought. I love that you guys use technology as far as your graphing calculators, and I want you to use them the correct way. So now we have a natural logarithm of x minus 2, and that one was shifted horizontally still, but this time to the right 2, which means my horizontal asymptote, vertical asymptote, instead of being at x equals 0, it's now going to be at x equals 2. Oh man. This is getting ugly. Ugly, ugly, ugly. which even without knowing what the graph looks like, I know that means my domain will go from 2 to infinity. However, I think now would be a good time to use my technology, get a couple of points at least. Unfortunately, with natural logarithms, you're not going to find a whole lot of good points. I believe it was x minus 2. I remember it shifting to the right. And then if you go to your table, I see that the asymptote is at 2. And we're slim pickings for some points here, guys. 3, 0. And that's kind of it. So 3, 0, and then I'm going to graph like 10, and then just above 2. Oh, 2. Hello, 2. So that's not great. Couple of things that I would be critiquing about your graph, which I know is ironic that I would critique anything about your guys' graph. Oh, by the way, the range is negative infinity to infinity. I would be looking for you somehow marking where the asymptote line is, preferably with like a highlighter. That would help. I would be looking for that little tail to swoop down. And I also am, it can't be sloppy. So like this tail can't come across the asymptote line. You got to be careful about that. Arrows on both ends. These are all very obvious things that I would expect you guys to do. And for me, I know I'm challenged when it comes to graphing, but you know, I do what I can. All right, this guy has been transformed, but this is outside of the logarithm, which means it's a vertical transformation. So it's been shifted down 5. Now, a common log this time. So close the log, whoops, put an X in there first. Then close the logarithm and shift it down 5. I see that it's been shifted down 5. Now, I'm still going to run into it doesn't do a great job of graphing, and there's not a whole lot of good points. One thing I will notice is that there seems to be an asymptote starting at 0 there. So x equals 0, 1, negative 5, 1, negative 5, and 10, negative 4. Okay. 1, negative 5, and 10, negative 4. And then the asymptote, the down 5 does not affect a vertical asymptote. So it's still going to be at x equals 0. And then we're all in for a treat when you try to graph something. Ugh. You know what? That was not the worst one I've ever graphed, okay? That was actually pretty stinking good. All right, so your domain, again, starts at approximately getting close to 0. Doesn't hit 0, though. Goes forever to the right. And as far as range goes, it goes forever. Negative infinity to positive infinity. It goes up really slowly right here, but it does technically go up forever. So we've learned that our calculator is not amazing at graphing logarithms, and everybody understands that. So with that being said, we should be able to come up with some conclusions about logarithm graphs without having to touch the calculator. So the transformations are exactly the same transformations that you know about, right? So this guy right here, H, is the horizontal transformation, meaning right and left, and it's got that built-in negative. K is your vertical transformation, meaning up and down. Oops, that's vertical. And then a couple of connections that we should be able to make now. The vertical asymptote is at wherever the shift is for the horizontal piece. Because you think about a vertical line, the thing that moves a vertical line is shifting it right and left. So a vertical asymptote is always going to be at x equals h. The domain will kind of start at that h, except with a parenthesis, right? And go to infinity. Now there's some special cases of logarithms that I am completely ignoring, and that's okay. And then the range goes from negative infinity to positive infinity. So just like with our exponentials, I would bust out the highlighter, and I would like to point out to you that there are some things that go together. The horizontal transformation affects where the vertical asymptote is lined up. It affects the start of the domain. All those things should match, okay? Every one of them. Oops, and I should highlight right here too. So just like with exponentials where the k made all the difference, in a logarithm, the h makes all the difference. So that's a nice little connection to those two inverse functions that really have a lot to do with each other. They just happen to be opposite. All right, good luck, everybody.